My name is Justin Scherbring, and this is my presentation for the analysis of adaptive forward error correction for best effort wireless sensor networks. So an overview of the project is the paper was based off the 802.15.4 wireless standard. It uses the OQ-PSK modulation demodulation scheme, and that standard also uses the CRC and ARC protocol for error detection and error control. What the paper is presenting is an idea to, instead of using the CRC and ARC protocol, it's using adaptive forward error correction, or AFEC algorithm, to prevent errors from occurring and reduce the number of retransmissions that occur between two nodes in the wireless network. How that works is the transmitter keeps track of the number of ACKs that the receiver is sending back, and if it receives a certain number of ACKs in a row, it decreases the amount of forward error correction, because that means the channel is good and you don't need as much redundancy to get your message through. So your throughput increases when the channel is good, and if the channel is bad, the transmitter increases the number of forward error, or increases the level of forward error correction. The only change that needs to be made to the additional standard is a field needs to be added to the packet for the receiver to parse out and then detect what level of FEC is being used for that packet. So on the left here you see the algorithm description of the AFEC algorithm, and the CT is the transmitter counter and the L variable is the window size. So every L packets, or every 20, is what we use, or what I use in the simulation. You compare the number of received packets to number of transmitted packets, and if it's over a threshold, you can increase the level of FEC by a certain increment, or if it's less than that threshold, you can decrease the FEC by a certain increment. So that's what that algorithm is. It's fairly simple. The paper did some exploration for what you should set that threshold to, what you should set your window to, and then again the strategy for your increments. So on your right hand side you can see the strategies are U1 D1, which would be your increment up by 1, your increment down by 1. U2 D1 would be increment up by 2, down by 1. And the reason for those different strategies would be for when your channel changes, you try and adjust for it accordingly, so you're not spending time waiting for it to change and going through the various levels of FEC. If your channel drops off instantly, you want to be aggressive in the amount of FEC you change by. The switching thresholds is just for what you're comparing against, and I used 0.2 for the switching threshold because running a complete simulation at 0.15 and 0.25 wasn't possible due to the time constraints. The strategy I used was U1 D1 just for simplicity's sake as well. So the system model was split up into 3 functional blocks: the transmitter, the channel, and the receiver. The feedback path is between the receiver and the transmitter. So the transmitter is then split up into 5 sub-functional blocks. It begins with the AFEC control logic, and then it goes to the data generation, and then it goes to a adaptive FEC encoder, and then the packet formation and modulator. The AFEC control logic is really the crux of the simulation and the paper. That's where all the adaptive algorithm is located, and that's where all the core of the paper and simulation resides, and it uses the feedback path from the receiver to keep track of the number of ACKs and whether the packet was received correctly. After that, it's random data generation in MATLAB. The FEC encoder is just a simple FEC encoder provided by MATLAB. Packet formation takes a repeated pattern for the preamble, a constant start of message delimiter, and then it fills out whatever the FEC type is from the control logic and puts that in the packet. And then the modulator is again a simple modulator from MATLAB. So the output of the transmitter is some complex data samples, baseband data samples. So the receiver receives these complex baseband data samples from the after it's been ran through a channel, and the simulation just used an AWGN channel. So noise was added, but the receiver receives these noisy complex baseband samples, uses the demodulator from MATLAB, and then comes up with baseband data bits, figures out the type of FEC that's being used, and then chooses the proper FEC decoder, again provided by MATLAB, and then detects if there's been any errors in the data payload of the packet. If there are no errors, it sends back an ACK to the transmitter, and if there is an error, it doesn't send anything back, and the transmitter resends the same packet again. So here are the results for the legacy on the left, and the current results that I obtained in my simulation on the right. As you can see, we don't get the gains for the various levels of encoding in the lower noise areas, from -2 to 2, but the ordering from in the higher noise areas is still there for the various encoding rates. And the most important takeaway from these two data sets is the adaptive algorithm, the black on the right and the red on the left, both fall between the 15.9 and 15.7 encoding schemes in both simulations. So again, that's the main point of the paper, is to prove the advantages and gains that can be achieved by using this adaptive FEC algorithm. Just because we don't see the gains in the lower signal to noise ratio environments, I think that could be due to the differences in the simulation, mainly the AWGN channel being used in my simulation versus the Rayleigh channel used in this simulation in the paper. Also different levels in the packet threshold or the strategies that were used. All those variables combined could add up. So I think the important takeaway is that the same general trend between both data sets are there, and the adaptive algorithm does prove to have an advantage over any static FEC encoding. So the conclusion is, if you look at the AFEC algorithm over unencoded schemes, there can be a 6 dB of gain that can be achieved at certain noise levels. It's relatively simple to implement. It's some if-then statements, then you have two counters that keep track of your number of received packets and total number of packets. So it was fairly simple to implement. It was more figuring out the FEC and MATLAB were the biggest struggles. But again, due to the last minute changes in the group assignments and who's responsible for what, wasn't able to implement all the finer details of the project. So that's where I see some of the deltas residing in the results. But again, the overall trend of the data is present, and the gains that the paper talked about for the adaptive FEC algorithm is still present in this simulation, and I think those gains can be verified. So here's the simulation example. The simulation takes over an hour to run, so when you do all the different static FECs and then all the different, and then the unencoded and the adaptive FEC, just because you're trying to send 90,000 bytes, and in the low signal to noise ratio, you're retransmitting a lot of times, so you have to have a timeout value, and it just takes a long time to run. So that's why this simulation was only I think 55 seconds, but it takes an hour plus to run the entire simulation as a whole. The goal of the project was to see the advantages of an adaptive forward error correction for that wireless standard, and I think that was observed in the results that I obtained. So thank you.